test. Okay, it's working. All right, well, I've written when I show you mine, I've got the minimum. Like I tried to write the bare minimum. So if you want to try to hit the bare minimum, you can do that. Don't give me too many words. Then I have to read them. Nothing. Looks like the back row is just polishing things off. So if you are done, I know the front row probably needs a little bit more time, but feel free to pass your stuff over. I'll figure out who's done and who's not. All right, thank you. Nice, excellent. I'm not rushing you, am I? All right. I'm just sort of scanning right now, trying to figure out how people are doing. Doing okay? Got an A? 100%. Good. I'll use yours as the key. All right. You doing okay back here? Look good? Yeah. Very nice. I like it. Beautiful. Some of you are still meditating on that last one. Remember, use the bigger of the two things in the denominator. You'll be okay. Are you still ruminating over here? Very nice. That's great. All right. You get it? Excellent. Nice work. All right, now you should try to finish up. So it is time to panic. So try to get her done. I'll come get what you have in just about a minute. A peek, I see. Some of you have answers. You just don't want to give them to me. Nice, very nice. Well done. Ooh, that looks good. All right, you're all set. Good job. All right, good job. Got something? All right, very nice. Oh, wait, are you still working back here? Wow, what is?
This is just work.
Oh, that's your homework.
Yeah.
Amazing. It looks so precise. Are you engineering?
Yes.
Oh, looks like you'll do great, at least with your precision.
I write small.
Yeah, looks good. All right, what do you think? Oh, look, you have an answer. You just don't like your answer?
Yeah.
Why not? No, I like your answer. Don't erase. Give me that. Give me that. I like that. Just put something there. No, this is good. Here, this is good. Let me keep it. All right. Oh, one more. Here. You got something? All right. Excellent. Anyone else? Oh, a couple over there. Sorry, I missed you. If you want, I can stand over you as well and make commentary. I don't need to make commentary. Good. All right. Do I have them all now? All right. Let's do this. So, first one. Hopefully, everyone got that one, because it was basically the same as the one that you did on your homework that we went over just a minute ago. So whoever asked the question, well done. You picked well. Yeah, the one on our homework had a 1 here instead of a 2, but it's basically the same. So 2 over radical n minus 1 is bigger than 1 over radical n. Yeah, so I wrote basically the bare minimum. So I probably should have written more, like say that p is less than 1, and so this diverges. But if you want to know what the very bare minimum is, this is it. So there you go. Okay, the next one. Next one, once again, hopefully it was super obvious, but maybe not. So that thing, I just was like, well, if you get rid of all of this stuff, you'll have a bigger fraction. So there you go. That thing converges, so because p of equals 2. So once again, this is the minimum. If you write a little bit more, it's fine. I just wanted to show you, like, this is what I'm looking for when I'm reading your exams or your quizzes. I'm sort of scanning. Do they have this? Do they have this? Do they have this? And sometimes I even put check marks where I found the stuff that I'm looking for. And then the final one, this is the one that caused a little bit of grief, I guess. Wait, do I have another version? No, I don't. Oh, well. So I guess there's my work there. So if I get rid of the radical n, it actually makes the denominator smaller, which makes the whole fraction bigger. So you have this. And then this is a geometric series. So I know I threw a geometric one in there, but you should know the geometric series. So this is geometric. It converges because r is 1 over pi, which is less than 1. Well, between 1 and negative 1. So there it is again, the bare minimum. So it should be what, diverge, converge, converge? Yeah, and give me some reasons. So you can't just say diverge, converge, converge, because then I'll just be like, well, why? How do you know? Okay, we do need to move on. So we have a couple of things we're going to do. First thing is I will pull this back up if I can find it. Hold on a sec. Where is it? It's right here. Oh, yeah. Okay, so we have this series flow chart. You may be making one as well that's better than mine. And I think I mentioned that that I forgot something at some point, but we'll bring it back in here. So let's just remind ourselves of these. Geometric, if you have something that's geometric, do you recognize what that is? Do you know what geometric means? If you have a geometric series, does it converge or diverge? It just depends on what the common ratio is. And this is super confusing, I realize, but with the P series, you end up with a different rule because it's a different type of series. But if you have a P series, then you want the P to be bigger than 1. If it's a geometric series, you want the common ratio to be small, between negative 1 and positive 1. So there's those. Then this, I probably should have put at the front, but well, there it is. And this is the thing that I don't know if it got covered in the homework or not, but it is this basic rule that if you have a series where the terms don't go to 0, so if the terms don't go to 0, then for sure this will diverge because you keep adding numbers. And if the limit of the terms is not 0, it means you're adding big numbers. Like maybe they go here. I know I probably have examples of this, but here, let me just show you a quick example. of a series that you know for sure will diverge. So if we have, how about this? Let's do this. The sum of 1/2 plus 1 over 2 to the n. Okay, good enough. Let me add these together real quick. So what's that going to be? That's going to be 2 to the n minus 1 plus 1 over 2 to the n. Is that right? Because if you want to make a common denominator. Yeah, that's right. Okay, so this particular series, the limit is 1/2. So the limit as n approaches infinity of 2 to the n minus 1 over 2 to the n is equal to 1/2, which is not equal to 0, and so this diverges. So this was in the introduction to series. It was just a little fact, but it's useful at times. What it means is that if you have a series like this, there's no sense in worrying about comparisons or anything else. You just like, that diverges. I don't have to do any more work. Now, sometimes you don't notice this sort of thing, and you might say, well, I don't notice, so you might have to do a comparison test. But if you happen to notice that the limit is non-zero of the terms, then you can just say, oh, it diverges. So that's what this one is. So that we talked about integral tests, and I don't have the actual integral test over here, but you know what that is. So if if you're making your own flow chart, I think in the past I've actually included in my flow chart the actual integral test over here. So you could sort of do that, whatever. But that's up to you if you're making one of these. Now we have the comparison tests. Can you compare this to something? So you have the direct and limit comparison tests. So we'll do the limit comparison test today. It's not going to take too long. And then Monday we get to, no, not Monday. Today is Wednesday, isn't it? Friday. Friday we get to do the alternating series test. So that's this here. So that'll be the next one. Is it alternating? We'll have to talk about what that means. Maybe we'll have time today to so this is a yes, and this is a no. So no, this is a yes. Okay, so we'll talk about what alternating series are in a bit, but we need to get back to our limit comparison test. So here's the limit comparison test. I don't know if I mentioned this already or not, but the basic idea is, yeah, we did do this, didn't we? We had this. So basically, it's when you think that you can compare two series, but you can't figure out which one is bigger, but you still want to use the two as like a comparison, then what you can do is you can just find a limit. As long as the limit is finite, non-zero, then it marries those two and they have the same fate. So as long as you can find a series that has this limit that is non-zero and finite, then basically the two series will have the same fate. So let's actually do this with a few, let's see, yeah, I've got them here. So let's do this with a few series. So here's some examples. I have this series. And so if you have that series, what would you want to compare that to using a limit? So once again, when you're doing this, when you're trying to figure it out, I think I mentioned this, you find the biggest thing in the numerator and the biggest thing in the denominator, and you make a fraction out of those. That's usually what works. So let's go ahead and find someone to tell me what's biggest. You go ahead and take a guess. Oh wait, let me fix my attendance first. I have someone that snuck in. So you have plenty of time to figure out what's biggest. All right, now we have it. Eli knows. Eli, what's the biggest thing on top here? Yeah, I know. There's only one thing. What about on the bottom? What's the biggest? Yeah, 5n, right? Yeah, e to the negative n is actually pretty small when you put anything other than 0 into that. So e to the negative 1 is like about 1/3. E to the negative 2 is about 1/8. It just gets smaller and smaller. So what we're going to compare that to is 1 over 5n or just 1 over n. Here's the thing. When you're doing a limit comparison test, it doesn't matter, like the constant, like the coefficients don't matter. You can leave the 5 there or you can not leave, doesn't matter. So let's do a limit. So here's how the limit comparison works. Limit as n approaches infinity of this fraction. Pick 1 to go on top. And I've done this enough times that I know what's going to work better, but it doesn't matter. It just means you'll be doing a little bit more work than me if you choose the other way. 5n plus e to the negative n. That's going to equal this limit. So there's going to be some algebra involved. So give me a minute here. I probably should have made you do this, but too late now. Let's see, get rid of this. It should be 5 plus 1 over n e to the n. That's better. Okay, so just as a quick word of what I just did, I took the this and separated into 2 fractions. And this is why this way is easier than the other way. If you flip this, it makes it a little bit harder, but it's still doable. It's not hard, not terrible. You could use L'Hopital's rule or something. Okay, so we've got this. I've separated this into 5n over n, which is 5, and e to the negative n over n, which if you take that negative n, it means that e to the n belongs in the denominator. So if you trust me, then you know what this limit is. In fact, here I will do the first part, the 5, there. The limit of as n approaches infinity of 5 is just 5. And then Carson knows what the limit as n approaches infinity of this is, don't you? It's just 0, because you've got 1 over a huge number, which is 0. Very nice. So that's equal to 5. So here's what the limit comparison test says. It says that since there is a limit that is finite and non-zero, 5 is finite and it is not 0, then those two are linked. They are linked. Their fate is sealed with one another. So these are linked. And so now we just need to know, what about that simpler one? Hayden, this one over here, does this converge or diverge? You can either call this the harmonic series, or you could call it a p-series. No, you got it. You got it. It's right there. It's just a little to the left. Just a little to the left. There it is. It diverges. Very good, because either you could say, hey, this is the harmonic series diverges, or you could say this is a p-series with p equal 1, which diverges. So however you want to call it, I'm going to call this harmonic because it sounds cool. Harmonic, you know, it sounds like someone going and playing music. Oh, sorry, I put an A at the end. Okay, harmonic, so it diverges. Okay, so there. So there is the, what? Okay, well, when it equals 1, then it's harmonic, diverge. Nice. Okay, so far so good. Any other questions about this one? Let's do another one. Here's the next one. I'm going to erase my ink, by the way, so you've got a few seconds, and it's going away. Gone? Okay, so this one, what do I want to compare that to? So let's pick a volunteer to say, well, I'll give you a minute to jot it down if you want to, and then pick the biggest thing in the numerator and the biggest thing in the denominator. All right, Simon, you know what's biggest, don't you? What are we comparing this to?
1 over n squared.
Yeah, 1 over n squared. And you could leave the 3 there if you want, or it doesn't matter. The 3 is irrelevant. to this particular test. So I usually omit it because it feels more fun to me, but you can do whatever you want. Okay, so let's actually set up this limit. And I think you're probably noticing the pattern is that if you put the simpler series on top, usually life is going to be a lot easier than if you put the simpler series on the bottom. Actually, in this case, it really doesn't matter. So give me a minute here. So there it is. So yeah, in this case, oh, I was going to have you do it, but it's too late now. I got in this case, it doesn't matter because you have two polynomials. So if I had this flipped, I know it looks a little bit different, but you'd have 1/3 instead of 3. But yeah, either way you cut it, this isn't too difficult to do. So taking the leading coefficient, I was going to pick someone to do this. Sorry, I jumped the gun. It's 3. Everyone knows it's 3, right? Yeah, of course you do. Okay, let's get to whether this converges or diverges. Thomas knows this one over here, does that converge or diverge? It converges. Why? It's a P series. P is greater than 1. Very nice. So this thing converges, and we have just proved, converge. So we have just proved that those two are linked. Their fates are sealed with one another. And so because this one converges, that one for sure converges. Eli, what do you think? Oh, however you want to do it is fine, but I'm kind of using the cheater method, which says that if you have a polynomial with the same degree, and you just take the leading coefficient on the top, leading coefficient on the bottom. A more correct way to do this would either to be divide everything by n squared, or to use L'Hopital's rule twice, which also works, but it's just longer. So yeah, so either way works. But yeah, you'll always get 3 as your limit. Yeah, and if we had this flipped, of course, you'd have 1/3. But as long as it's non-zero and finite, then those two are linked. All right, any issues, questions, concerns about that one? Yeah, what do you think, Red?
What is the relation between 3 and y converges?
The relation is that the 3 is not 0 and it is not infinity. As long as what you get down here is not 0 and is not infinity, then, so I don't care what number this is. This could be 52, or it could be 99, or it could be pi. But whatever number I get here, as long as it's not 0 and it's not infinity, then that attaches these to one another. They're gonna have the same end. They will either both converge or both diverge. So that number really doesn't matter. Just all that matters is that it's not 0. Anything else before we do the next one? All right, these aren't too bad, are they? Okay, so let's get rid of this stuff. Give me a sec. Sorry, it's gone. You can always watch the video. Okay, so here's the next one. These are all P series. Is there I hope the next, let's see, I think I can see. I guess the last one's not a P series, I think. Yeah, the last one's not a P series. So we can be thankful for that. This one's a P series though, so boring. We've done this. But go ahead and see if you can do this. What are we going to compare this to? Let's find a volunteer. So I'll give you a minute to jot it down. All right, Andrew, what do you want to compare this thing to? Very nice. So he's even done the algebra for me. So probably you're looking at this saying the biggest thing on top is n squared, the biggest thing on bottom is n to the fourth. N squared over n fourth is exactly what he said, 1 over n squared. Very nice. So here's that. And so that's going to be my comparison. Let's do a limit. By the way, just before I go on, I just want to point out that this one, you could have used a direct comparison because that over there is actually less than this over here. So I don't know if anyone caught that, but it doesn't matter. We're going to do a limit anyway, just to practice. So set up your limit. Limit as n approaches infinity of, let's see if I can get this right, 1 over n squared over radical n plus n to the fourth. Whew. Let's see, how does this work? Flip the bottom, multiply. So I have limit n approaches infinity of radical n plus n to the fourth all over n to the fourth. Okay, at this point you might just write down the answer, but I'm gonna do one more step just because I want to. Limit as n approaches infinity of radical n over n to the fourth plus 1. There. Okay, so either way you want to do it, either doing it this way or that way, I don't care. You come up with your limit, the limit that you think is the correct limit, and then we'll pick a person. All right, you've got one? Hopefully everyone's got one. Darren, do you have one? Do you know what this limit is going to be? Yeah, it's just 1, because the limit of this is 0. So either way you cut it. If you do this way, you might think, oh, why don't I just do the whole polynomial trick? The reason why I didn't want to do the polynomial trick is because technically this is not a polynomial. That's a square root, not a polynomial. But whatever, if you do the polynomial trick, you're like, well, the highest degree here is 4, and the highest is here is 4, and it's 1 over 1, good. Or over here, you say, okay, radical n over n to the fourth is 1 over n to the 3.5, and the limit as n approaches infinity of 1 over n to any power is 0. So that ends up being just 1 because of this one right here. Okay, so those are linked. Those are going to be linked. So whatever happens on the right, it will be true on the left. And Americo, what is true for the right? Does this converge or diverge? What did you say? Oh, it converges. That's right. We just did it. It converges. So this one converges, which means that one converges. We're all happy. So this one, it's a P series. Series P is equal to 2. This converges. Okay, one more, and I promised that the last one is not a P series. So that's exciting because we get used to a certain thing and then you think that they're all the same. So let me just give you a minute in case you want to jot anything down because I'm about to clear. I know. I should have put these all on different slides, but I didn't. I don't know why. Okay, clearing it out. There it goes. Okay, last one. Let's see. This one's fun. So take a minute and write down what you think. I just realized I don't like the minus in the denominator because that gives me negative numbers. And so let's just make that a plus. It doesn't matter. It doesn't matter, but let's make it a plus just so that we won't have to deal with negative numbers. All right, well, let's compare this to something. Braden, what would you like to compare this to using a limit? N squared over 2 to the n. Yeah, that sounds good because you're just taking the biggest thing in the numerator and the biggest thing in the denominator and making a fraction out of them. Now, the only problem with this is that this is not a P series and this is not geometric. So what are we supposed to do with that? Well, we're going to have to do something. So let's go over to Notability because I don't have enough room in the bottom of this slide. Give me a sec. I'm going to copy this. And so this is a weird, let's see, done. This is a weird one. Let's see, I'll put it down here somewhere. Because I'm going to use the limit comparison test and a direct comparison. So I'm going to do both. So if I have this, so here's how this is going to shake out. I've got, I'm starting with this. This is my goal. Goal is right here. But I don't know how to do that. And so I'm going to shift over to this. But that one I don't know, at least not yet, but I will soon. So here's how I'm going to do this. And this is a little bit avant-garde, or maybe just a little bit weird. It's not something that we're commonly doing, but it is correct. And that is this, that n squared, let me just point this out, n squared is less than 1.9 to the n power. Okay, that's not always true though. This is true when n is bigger than 6. Okay, so you can double check. Take your calculator. I know you don't believe me. And do 1.9 to the 6th power, and you get, yeah, this is, sorry, it took me a sec to think, is this right? Yeah. So 1.9 to the 6th power is 47, and 6 squared is 36. And you can do it for the 7, 1 point. Of course, once it's true, because this is an exponential function, it will always be true. 1.9 to the 7th power is 89. 7 squared is 49. So this is true as long as n is big enough. And that's all we need when we're doing these inequalities. And so I'm actually going to do a direct comparison. So check this out. N squared over 2 to the n is less than 1.9 to the n over 2 to the n. As long as n is greater than or equal to 6. So eventually this will be true. And that's all you need to be able to do a direct comparison. And so that's true. And 1.9 to the n over 2 to the n is the same as 1.9 over 2 to the n. And so let's talk about this. I'll even start at 6 to make everyone happy. So what kind of series is that? Emily, do you know what kind of series when we categorize these? What is that? It is geometric. That one's geometric. And so there should be a common ratio. So Christopher, what is the common ratio for this geometric series? 1 point. What does that tell us? Does this converge or diverge? Yes, it does, because this is less than 1 and bigger than -1. This thing converges, and so this converges. So check it out. It almost feels like when you have to do L'Hopital's rule multiple times, this converges. And because of the direct comparison, because of this one will converge. Oh, we still haven't done our limit, have we? We better do a limit to get to our goal. But I think you know what the limit's going to do. Limit as n approaches infinity of n squared over 2 to the n all over n squared plus 3n minus 1 over 4 plus 2 to the n. Okay, so this is going to be ugly. Limit as n approaches infinity. Give me a sec here. Let's see, 4n squared plus n squared times 2 to the n over n squared times 2 to the n plus 3n times 2 to the n minus 2 to the n. Wow, that's ugly. Okay. Okay, let's see if we can make this a little prettier. So let's separate this into 2 fractions. Since I have this plus up here, I can do this. So this is a little bit more complicated of a limit than we've had already, but I think we can conquer it nonetheless. So I'm going to separate this into 2 fractions. I just realized that it would be easier if I didn't have to write 2 to the n so many times. So I'm just going to take this, just factor out the 2 to the n. So plus this limit, because limits work this way. You can add limits together. N squared times 2 to the n over n squared plus 3n minus 1. What is it, time to go yet? No, not quite. Times 2 to the n. Let's do this, cancel those. Okay, so we're going to separate this into 2 different problems and deal with them individually. Okay, so the one on the right is easy. Let's deal with the one on the right, and then I'll deal with the one on the left myself. Maggie, what do you think of this one? if I get rid of the 2 to the n, you just have polynomials. Do you know what the limit of this fraction is? It's just 1, right? Because you're taking the leading coefficients because these are the same degree polynomial. Very nice. So this is going to be 1. This one is a little bit more complicated. So why don't I wave my hand a little bit and just mention that what you could do is you could use L'Hopital times 2. So I don't want to actually do it, but let me just explain what's going to happen. When you do L'Hopital times 2, here's what you can sort of imagine. The first time you do L'Hopital, so because you have infinity over infinity. First time, let's just focus on the numerator. First time you do L'Hopital, you get 8n up here and some garbage down here. The second time you do L'Hopital, you just have 8 and some garbage down here. So it's the garbage that's painful, but it's going to be the product rule, and you're going to have 2 to the n. Derivative of 2 to the n is natural log of 2 times 2 to the n. But whatever you have, you'll have a constant on top after 2 L'Hopital rules, and an exponential function on the bottom. And so after 2 L'Hopital's rule, you'll have basically the limit will be 0. So 0 plus 1. And I know I'm kind of waving my hand a bit there, but you could do it. You could go on to Desmos and say, give me the derivative of this twice. Do the derivative of this twice. You'll get 8 up here. You'll get something nasty down here. But whatever it is, the limit will be 0 over, well, 8 over infinity, which is 0. Okay, so anyway, the final answer is that. We're done because this one converges, which means these two are linked, and this converges as well. And that makes us all happy. Okay, so on your homework, you're going to be doing something similar to this, and do your best. Come up with the thing that you're going to do the limit for, and then we'll see you on Friday. So I'm going to stop the recording in case you want to come chat. Otherwise,